Hi class, in this video today we are talking about heat transfer and enthalpy. We are starting what is called thermodynamics, and thermodynamics is really kind of 2 units within AP chemistry, but we're focusing right now just on the heat aspect. And what I want to start with is this. Many of us have probably used hand warmers before, but do we know how they work? Now, we might have an idea as to the fact that by shaking it and activating something, that's going to make a reaction take place, and that reaction gives off heat, and you would be right along track with that. That is what happens, but how does that function? Where does that heat come from? That's what we're going to look at within this unit. So we're going to start first with quick definitions. It's so important that we know the distinction between temperature and heat. Temperature is really just the hotness or coldness of a substance, right? We measure that average kinetic energy in Kelvin or degrees Celsius, but primarily Kelvin. Whereas heat is an energy flow. And because it's an energy, it's measured in joules. And heat always flows from a hot substance to a cold substance. That's how that thermal energy transfers. And it stops flowing when we reach something called thermal equilibrium, which is when the substances are at the same temperature. So even though we might use the terms interchangeably kind of in everyday life, they are very different. And that's really important because when we have two substances that are at different temperatures in contact with each other, right, they will eventually reach the same temperature. And that's because the energy will be transferred from the molecules that are warmer to the molecules that are colder. As we will learn in our next unit, that is all about collisions. That's all about the molecules and the particles actually colliding with each other in order to transfer some of that energy. But we're going to operate under this first law of thermodynamics, which is the law of conservation of energy. It says energy cannot be created nor destroyed. Okay, and when we're looking at heat and we're looking at how heat transfers between different components, we're going to look at it in 3 situations. If we have 2 objects that just have different temperatures from each other, right? You walk outside into warm air, okay? Or you put an ice cube down on a counter. We're going to talk about physical changes such as melting, and we're also going to talk about chemical reactions as well. So in chemistry, we want to be able to talk about and describe how heat flows from one substance to another substance, between objects. And so we use the term system and surroundings. Basically, we operate under the assumption that we are talking about the universe. We're talking about everything. And the universe is made up of this system and surroundings. And the system is pretty strangely defined. It's what we are interested in, whereas the surroundings is everything else. So if I'm talking about an ice cube and I put an ice cube down on a counter from the freezer, right, we know that ice cube is going to melt. Well, if the ice cube is the system, right, where is the energy coming from for it to melt? It's coming from the surroundings. And so this interchange of heat between systems and surroundings is what we want to be able to describe when we describe heat transfer. So if we have something we're interested in, like an ice cube, okay, that's our system. And that process is one in which it absorbs heat from the surroundings. The system is absorbing the heat. That's an endothermic process. So things like melting, things like liquid becoming a gas, a bond breaking. This is the most important thing, by the way, right here. Or a substance that just heats up, a substance that just absorbs energy, right? You walk from a cold inside to a warm outside, right? You're going to heat up. You're going to absorb heat from the outside, from the air, from the sun. That process is endothermic. It's when the system is absorbing heat from the surroundings. Whereas in an exothermic process, such as a campfire, and we have something that is giving off heat, that is going to be an exothermic process, okay? So the opposite here of melting, freezing, is exothermic. Condensation, the opposite of vaporization, is going to be exothermic. So is bond formation, and then so is when a substance cools down as well. So we do want to be careful when talking about whether or not a process is endo or exothermic, because it does depend on what the system is. If the campfire is the system and you are part of the surroundings, that's an exothermic process. But that's just something to be aware of. The other thing I want to mention with labeling things as endothermic or exothermic is that solutions, right? So when a substance dissolves in water, we get a solution. Solutions can be either endothermic or exothermic. It depends on the process. It depends on the bonds that are being pulled apart from each other and the interactions that are forming. And we'll get to that a little bit more in a couple of days. So then, what was that strange word at the beginning of the screencast? It's called enthalpy. Enthalpy is pretty much heat. So as scientists, when we do some reactions, we do them at certain conditions. And most of the reactions that we do are at constant pressure, atmospheric pressure. And so we call enthalpy the heat that is released or absorbed at constant pressure. Okay, so it's heat just at a very specific condition. And in chemistry, what we do is we measure the enthalpy change of a process. Okay, so we measure the difference from the beginning to the end, or the reactants to the products. And so this is a really good diagram right here. What it's going to do is it's going to tell us what we said on the previous slide, which is that for endothermic processes, they absorb heat from the surroundings, whereas in exothermic, the system gives off heat to surroundings. Except this time it's using it with this delta H, where delta means change, and the H is talking about enthalpy, the heat that is released or absorbed at constant pressure. So you can see that endothermic processes have a delta H greater than 0. That means that delta H is positive for endothermic processes, whereas for exothermic processes, delta H is going to be negative as a process. And again, what we're really doing in reactions in particular, of the 3 changes that we'll look at, but is that difference between the reactants and the products. And we'll look at that more in just a moment. But what this is telling us is that in an exothermic reaction, the enthalpy will decrease of the system, and in an endothermic process, the energy will increase in a system. Okay? And we will relate this very, very soon to breaking and forming bonds and the energies that are involved with those processes as well. Before we move to the next slide, just as a quick point, when we have a reaction or a change, a physical change, when we are talking about the system, if the system is absorbing this energy and it's endothermic, right, we use that word absorb, okay? When we say that the energy or the enthalpy is released, okay, that means that it's exothermic as a process. So just in terms of vocabulary, those 2 terms are really important as well. Okay, released is talking exo, absorbed is talking endo. Well, it wouldn't be chemistry if you weren't asked to try to model the change that occurs within a reaction. So just as a reminder to us, right, heat is a form of energy. So even though this is an energy diagrams, and energy is labeled here, we can really think about that as enthalpy, because in chemistry, the energy that we're measuring most of the time is going to be heat. So how can we measure heat flow for a reaction? Okay, now this is a combustion reaction. Combustion reactions, all of them are exothermic. And pretend that there is an arrow right here. You can see this is a balanced equation, okay? Same number of each atoms on each side. Now we just said that for an exothermic reaction, heat is released, energy is released. So does that mean that this should be higher than the original at the same point, or lower down in terms of where its energy is? Well, hopefully you agree it should be lower. Okay, and the reason why it should be lower is that energy was released. So that means that the enthalpy of the products, the final state, is at a lower energy than initial. And that difference between, that is the amount that is released. We would label our energy diagram something like this to show that the overall change, right, is going to be a negative change. It went down in terms of this y-axis, where 0 is right here. And so because the enthalpy decreased, that's an exothermic process. Now for an endothermic process, we would expect this to be higher than the reactants, okay? But since it's an exothermic process and all combustion reactions are exothermic, then that's going to be the case here. So then the final thing we want to discuss is how we can take this energy in reactions and how can we quantify it? How can we calculate the heat that is involved within different processes? So here's another combustion reaction that we have, okay? And for this combustion reaction, you'll also see that in addition to the balanced chemical equation, over here you're told that the enthalpy change for the reaction is negative 2,857 kilojoule per mole reaction. Now I want to talk about a couple different things here. Number one, this little circle up here, okay, that means standard. So oftentimes, again, in chemistry, we have standard conditions for things. This is not the same thing as standard temperature and pressure. This is called the standard state, in which the temperature is 25 degrees Celsius, and if there's gases, we assume all of them are at 1 atmosphere, and all solutions are 1 molar as well. Now, the second thing I want to point out is this kilojoule per mole reaction. What the unit of mole reaction refers to is it's saying for this reaction as written, okay? And so we will use that in some stoichiometry in just a moment, but this is the amount of kilojoules for these specific substances reacting, 2 moles of C2H6 and 7 moles of O2. So with stoichiometry, with different amounts, right, what if we don't have 2 moles and 7 moles, okay? What if instead we had half that amount? What if we had 1 mole and 3.5 moles of O2. What would the enthalpy be then? Well, if you guess that it would be exactly half the amount, that's correct. Okay, so enthalpy is a function that's an extensive property. It depends on the amount that's present. So if we have exactly half the amount of reactants, we produce half the amount of products, as you can see from this equation. It's going to release half the amount of energy as well. Okay, you also notice in this equation something different, which is that I've got a fraction here, and we're not supposed to have those. You will see that quite a lot within enthalpy questions in stoichiometry, and we'll talk about that a little bit more at a later time. But the last thing that I want to note is, what if the reaction instead was flipped? So what if instead of C2H6 and O2 reacting, carbon dioxide and water reacted with each other? What would the enthalpy change be for that reaction? Well, perhaps you were able to guess this one too. It would be flipped, okay? So if this direction of the reaction is exothermic, then this magnitude of the number, right, is going to be the exact same amount that we need to put into the reaction overall in order to make it happen. So in this case, the reaction would be endothermic, whereas in this case it's exothermic. And all we do when we flip the reaction is we flip the sign of delta H too. Okay, so then finally, what if we don't have those exact amounts? So what if I have this reaction and instead of having 2 moles of this and 7 moles of this, I have 38 grams of C2H6 and I have an excess of O2. I've got plenty of oxygen gas. What would the enthalpy change be for the reaction? Well, what I can do is I can use stoichiometry. Okay, so I can take my 38 grams of C2H6, I can go to moles of C2H6, and then I know if I have 2 moles of C2H6 in 1 mole reaction, then that's going to produce negative 2,857 kilojoules of heat. Therefore, I can use stoichiometry in order to help me solve this equation. And this is what it should look like. So your work should look something like this, right? Where we have 38 grams and we went from gram to mole. And then all I'm doing in this component right here is I'm going from the moles I have in the equation to 1 mole reaction, which is again just saying as the reaction is written. And then I know for 1 mole reaction is going to be negative 2,857 kilojoules. So you might ask yourself, if this step is necessary, could you just go from 2 moles here to negative 2,857 kilojoules? The answer is yes, you could. Sometimes this unit will not have mole reaction on it. It'll just say kilojoule per mole, or maybe it will specify it per mole of one of these components as well. Okay, so we want to make sure that we're comfortable with that and aware of that. But at this point, we can then plug it into our calculator. And so if I'm using appropriate significant figures, the answer should be 1,800 kilojoules. And with this, actually I left off one thing. You should either say negative 1,800 kilojoules, or you can say 1,800 kilojoules released. When you're saying released or absorbed, you don't need to specify the sign necessarily that comes before it. But if you don't say released or absorbed, you absolutely need to make sure you have the correct sign, okay? So either of these 2 answers over here are acceptable for your answer. But this is heat transfer and stoichiometry and enthalpy, okay? So we're going to do some practice with this in class, but please let me know if you have any questions. Thank you.